October the 22nd, 1707. A Royal Navy fleet, 21 ships, is running home from Gibraltar through gales and dirty weather, and its navigators reckon they are far out in the open Atlantic, west of any danger. They are wrong. Out of the darkness come the rocks of the Isles of Scilly. The flagship strikes and goes down in minutes. 800 men, the admiral among them. By morning, 4 ships have been destroyed, and somewhere between 1,400 and 2,000 sailors are dead, within sight of England. No enemy fired a shot. The fleet died because not one man aboard could answer the oldest question at sea. Where are we? Here is what you are probably thinking, because it is what almost everyone thought. This is a map problem. Better charts, sharper lookouts, more careful captains. But a perfect chart tells you nothing unless you know where you are on it. And in 1707, half of that answer was easy, and half was impossible. Latitude. How far north or south you are, you can read straight from the sky. Measure the height of the noon sun or the pole star, and you have it. Sailors had done that for centuries. But longitude, how far east or west you are, the sky refuses to give up. Because the Earth is spinning, whatever the sun does over your head at noon, it does over a ship 500 miles west of you identically a little later. Same sun, same sky. No answer. So crews kept a running guess instead. Throw a knotted rope over the stern, count the knots as they pay out, estimate the currents, and hope. Every day, the guess drifts further from the truth. Chevel's navigators' last reckoning had put them 200 miles from those rocks. So if the sky refuses to tell you longitude, what will? The answer is hiding in something so ordinary you would never suspect it. The Earth makes one full turn, 360 degrees, every 24 hours. Divide, and the planet rotates exactly 15 degrees each hour. That is not trivia. That is a coordinate system. Because it means time and place are the same thing. Watch the sun from your deck, and you always know local time. Noon is simply the moment the sun stands highest. Now suppose you also carried a clock, still set to the time back home in London. At the instant of your local noon, you look at it, and it says 2 in the afternoon. Home is 2 hours ahead of you. 2 hours at 15 degrees per hour. You are exactly 30 degrees west of London. That is the entire secret. Longitude was never a map problem. It is a clock problem. All you need is a timepiece that keeps home time faithfully, month after month, on a moving ship. And in 1707, that idea was a joke. Why a joke? Because the finest clocks on land kept time with a swinging pendulum, and a pendulum on a rolling, pitching ship is useless. Worse, metal expands in tropical heat and shrinks in northern cold. Oils thicken and thin. Damp corrodes the works. At sea, all of it together threw even the best timekeepers hopelessly off. And remember, every 4 minutes of error is a full degree. 60 nautical miles at the equator. So in 1714, Parliament stopped waiting. The Longitude Act offered up to £20,000, millions in today's money, for any practical method that could find a ship's longitude to within half a degree. Run the arithmetic across the 6-week test voyage to the West Indies, and that means a clock that gains or loses no more than about 3 seconds. A day. For 42 days on the open ocean. Nearly every learned man in Europe expected the answer to come from the sky, from astronomers, from the moon. Nobody expected it to come from a carpenter's bench in Lincolnshire. John Harrison built his first pendulum clock in 1713 at 20 years old. He was a joiner, a carpenter's trade, with no training in clockmaking at all. So he built the clock the way he knew how, almost entirely out of wood. And it worked. By his 30s, his land clocks were accurate to about 1 second in a month, extraordinary for the age. Then he heard about the prize. In 1735, Harrison carried his first sea clock to London. H1, a strange, beautiful machine of brass and oak with no pendulum at all. Instead, two balances that swing against each other, linked so that the roll of a ship cancels itself out. On the trial voyage home from Lisbon, the ship's master reckoned they were approaching one headland. Harrison, reading his machine, said no. By the clock, they were 60 miles from where the ship's guess put them, bearing down on a different point entirely. Harrison was right. The Board of Longitude finally had a serious candidate. And then Harrison did something almost nobody does. He looked at his own triumphant machine and told them it was not good enough. The board paid him £500 to try again, half up front. Harrison went home and built H2, then found a flaw in its very design and refused to let it go to sea. So he started over. H3. He worked on that one machine for 19 years. 19 years. And along the way, he invented, among other things, the bimetallic strip and the caged roller bearing. Ideas so good, they are still inside machines around you today. But the clock itself never met the mark. A lesser man stops there. An obsessive does something stranger. He throws the whole idea away. In the early 1750s, a pocket watch built to Harrison's own design surprised him. It kept far better time than any watch was supposed to. Watches had a reputation as trinkets, pretty and unreliable. But a watch is small. A tiny, fast oscillator beating hard might simply shrug off the lurch of a ship in a way his great heavy sea machines never could. The answer to the hardest engineering problem on Earth might fit in your pocket. H4 does not look like a machine that changed the world. It looks like an oversized pocket watch, 13 centimeters across. Inside, a heart beating 5 times every second. Bearings cut from jewels, even diamond, to defeat friction. And a strip of 2 bonded metals that flexes by itself to cancel heat and cold. In 1761, Harrison was 68. His son William carried the watch aboard a ship bound for Jamaica. 81 days, salt, damp, storms, the endless working of the hull. At the other side of the ocean, they checked H4 against the known longitude of the island. Allowing for its declared daily rate, it was out by just 5.1 seconds. 5 seconds in nearly 3 months at sea. An error of about 1 nautical mile, more than 20 times better than the prize demanded. The 20,000-pound question was answered. The prize was won. Except that it wasn't. And the fight over why, that still echoes inside the phone in your pocket. Because while Harrison was building clocks, astronomers were solving the same problem with the sky after all. The moon slides against the background stars like the hand of one great celestial clock. Measure the angle between the moon and a chosen star, look up where the moon should stand at each hour of London time, and you can squeeze home time out of the heavens, no clock required. This was the lunar distance method, and its champion was the astronomer Nevil Maskelyne. Be fair to him, it genuinely worked. It needed no delicate, expensive, one-of-a-kind watch. And to a board dominated by astronomers, it looked like science, repeatable, mathematical. While one perfect run to Jamaica might just be luck. A fair worry, honestly. So the board demanded a second trial. 1764, Barbados. And the expert sent ahead to fix the island's true longitude by the heavens was, awkwardly, Nevil Maskelyne himself. H4 crossed the Atlantic again and came out 39 seconds off after 47 days. 3 times better than the prize required. Surely, now, the money. The board's answer came in 1765, and it broke the old man's heart. Half the money, £10,000, and only after he surrendered the watch and explained every secret of its insides to a panel that included his rivals. The other half? Only when other makers proved they could copy it. And Nevil Maskelyne had just been appointed Astronomer Royal, the nation's referee of longitude. Now judging a contest he had a horse in. H4 was handed over to the observatory at Greenwich, and after 10 months of testing under Maskelyne's supervision, the published verdict was blunt. The watch had not performed well. Harrison was in his 70s. He had given the problem 4 decades, and his life's machines now sat in other men's custody. The message from the establishment amounted to, "Thank you, old man. That will do." But Harrison had one move left, and it went straight over all their heads. Nearly 80, Harrison built one final watch, H5, and appealed to King George III. The king loved instruments. He kept a private observatory at Kew. He heard the family's story and, as Harrison's son told it, burst out, "By God, Harrison, I will see you righted." And he was true to it. For 10 weeks in the summer of 1772, H5 ran at the king's own observatory and kept time to within 1/3 of a second per day. With the king behind him, Parliament stepped in where the board would not. In 1773, it voted Harrison a further £8,750. Not the prize. In fact, the great £20,000 prize was never awarded in full to anyone, ever. But counting everything across the years, Harrison had received more than its value. 3 years later, he was dead at 82. Paid at last, but not yet proven. That proof was already at sea, on the far side of the world. So, who was actually right? The clockmaker or the astronomer? Honestly, both. Maskelyne's Nautical Almanac, first published for 1767, put pre-computed moon tables into any navigator's sea chest, and ships steered by them for decades. But there was a catch, and it decided the future. Working a lunar was hard. The raw calculation had taken even Maskelyne up to 4 hours. The almanac shortened the arithmetic, but it still demanded a skilled observer, a clear sky, and a visible moon. Harrison's method demanded that you look at a watch. In 1772, Captain James Cook sailed for the Pacific carrying K1, an exact copy of H4, made for the board by the watchmaker Larkham Kendall for £450. Cook was a master of the lunar method. He hardly needed a machine. 3 years among ice and coral converted him. In his journal, the greatest navigator of the age wrote about a watch the way you write about a shipmate. Our trusty friend, the watch. Our never-failing guide. The chronometer did not win because it was more elegant. It won because anyone could use it. Which brings us back to those rocks. Stand on the cliffs of Scilly today with a phone in your pocket, and it knows where you are, to within a few meters. And here's the quiet, wonderful part. It finds out the same way. Overhead, satellites are broadcasting time from atomic clocks, clocks that drift by only a few billionths of a second a day, millions of times steadier than H4. Your phone compares the time each signal carries with the moment it arrives, clock against clock, exactly as William Harrison once compared local noon with his father's watch. Light travels about 30 centimeters in 1/billionth of a second. So if you know the time finely enough, you know where you are, almost perfectly. We solved longitude twice, once with brass and diamond, once with cesium and orbit. And both times it was the same idea, the one those 1,400 sailors died without. Position is not written on any map. Knowing where you are has always meant knowing what time it is, somewhere else.